Hello everybody, welcome to this beautiful video. Curl up, grab a mug of cocoa, get comfy, and let's talk about integration odds and ends, aka integration miscellanea. So we just got a couple things that we need to wrap up before we move on to applications of integration. More trig rules and something called the average value theorem. So we have been using these derivative and integration rules for the three basic trig functions all year. They're up on the screen right now. We've been using them all the time. So this is nothing new. We've said in the past that it's nice to know the derivative and integration rules for the other three functions, cosecant, secant, and cotan, but we haven't actually said that we need to memorize those. Because technically you can figure out the derivatives and integrals of those based on the other three rules, but at this point you just need to memorize them. So we've got three new derivative rules and then three related integral rules, which are just the derivative rules in reverse. So the derivative of cotangent is negative cosecant squared. That's similar to, if you remember, the derivative of tangent is secant squared. Derivative of cotangent is negative cosecant. Derivative of secant is secant x tan x. If there's a function other than x in secant, so like secant x squared would be secant x squared times tan x squared times 2x. And then cosecant is similar. The derivative of cosecant is negative cosecant cotan times derivative inside. The integration rules just work in reverse. So a lot of times, so like on this test that we just did, So anyway, knowing these rules makes some problems just much faster. So you just need to add them to the list of rules that you can do, and there's really nothing that you can do except for just memorize them. Here's an example. I was just talking about this on the previous page. The derivative of secant x squared. So the derivative of secant is secant times tangent. So you get secant of x squared times tan of x squared times 2x, because that's the derivative of the function that's inside. If we're working the other way, we are trying to integrate cosecant squared of 2 theta. So here, this fits the pattern. 2 is the derivative of the inside function, so when we integrate, it will get reabsorbed. We have to remember from our new rules here that the integral of cosecant squared is cotangent. So you just get cotangent 2 theta plus c. So really, this is just a matter of memorization. In addition, we're also going to need to be able to take the derivative and integrate the inverse trig functions, so arcsine, arccosine, arctan. You can pause it if you want to write down these rules. These are also on the inside cover of the textbook, but they're just rules that you need to memorize. Here they are. Bloop. Oh, that's not the pen. Bloop. There's an example down here at the bottom. If we were trying to take the derivative of arccosine of 3x, so that's this rule right here. We take the derivative of what's inside the arccosine function. We get negative. We get 3, and then it needs to be negative, so it's negative 3. And then in the denominator, we have square root of 1 minus the square of whatever was in the arccosine function. So in this case, that's 9x squared. So it's just a pattern to memorize. Okay. We also need to be able to work the other way with inverse trig functions and do integration. So the trickiest part about inverse trig problems is being able to spot when you're looking at an inverse trig pattern in an integration problem versus just a reverse chain rule. So here we have on the screen here we have 2 integration problems. One of them is a reverse chain rule problem, and the other is integrates to an inverse trig function. So take a second and see if you can figure out which is which, and then we'll talk about how we could tell from looking on the next slide. Okay, so the first one is reverse chain. And the second one is inverse trig. And so one of the ways I could tell is that the derivative of the denominator in this first function is -5. And so when I look at the numerator is +5. That almost fits the pattern of having the derivative of the inside function in the numerator. If you rewrote this as here, 5 is almost the derivative of the inside function. It's only missing a negative sign, so I could just go bloop, bloop, multiply by negative inside and outside, and then do the reverse chain rule. We're only off by a constant, the 5. The second problem looks very tempting. Like, I'm like, oh, like, if I were just looking at this problem and scanning quickly, I might think it's a reverse chain rule problem because I can rewrite it like this. So it looks like the problem before. I've got 1 minus 25x squared inside of parentheses. It's raised to -1/2. I've got a 5 out front. The derivative of the inside of this function, however, is -50x. Right? So that x is problematic because I can't make an x appear outside here. So there's nothing I can do that's going to make this integratable for me, because we're not allowed to multiply inside and outside by a variable. We can only multiply by constants. So there's nothing. If I were looking at this problem before I knew the inverse trig rule, I would just think that this couldn't be integrated because we're off by a variable, not just by a constant. So anytime you are looking at an integration problem and you feel like it should be a reverse chain rule problem, but you're off by a variable, one of the things you want to think about is, oh wait, is this possibly an inverse trig pattern? That's one way to think about it, to notice it's an inverse trig problem. The other giveaway is that a lot in the function in the denominator, the numbers will usually be perfect squares. So 1 is a perfect square, 25x squared is a perfect square. So the pattern for inverse trig involves perfect squares being in the denominator. So if you are seeing a fraction, you see there's 2 terms and they're both perfect squares, and you can't quite figure out how to get the derivative of the inside function to appear here because it's off by a variable, not just by a constant. Those are all like warning signs that maybe you should be thinking about an inverse trig function. Other giveaway, obviously, if it's a multiple choice question, it's an integration problem, and the answer choices have inverse trig functions in them. That's obviously also a giveaway that maybe you should be thinking about inverse trig problems. Okay. So these are just some of what I was just saying here, hints to be able to recognize an inverse trig problem. You might want to put these in your notes. Obviously, on the quiz we're going to have coming up, it's only going to cover the rules that are in this presentation, so you're going to know things are inverse trig problems. The trick is going to be when we get to sort of like mixed review, and there's all different types of integration problems mixed together, being able to decipher which one is inverse trig and which one's reverse chain and which one's natural log and all that stuff. So keep these tips for when we are doing more mixed problems. Okay. Moving on to a totally second topic. So the average value theorem, not to be confused with the mean value theorem, which has to do with derivatives. We did that right after winter break. So this is the average value theorem. All right. So just a quick review, just about like how averages work. So if we want to find the average of a set of numbers, we add up all the numbers and then divide by however many numbers there were. So if I want to average the numbers 3, 4, 5, I do 3 plus 4 plus 5, and then I divide by 3. Yeesh. Handwriting's terrible. Blah, 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 blah. Okay, so the question we are looking at now is if I am looking at a function on a certain interval, what is the average y value? So in this example, we're talking about the function y equals x squared, so it's parabola, looks like this. What is the average y value for this function in between x equals 3 and x equals 7? All right. So one of your first instincts might be, okay, well, I'll just plug in 3, and then I'll plug in 7, and I'll average those two y values. So as it turns out, that's not the average y value, because this function is curved. So we have to figure out some way to take into consideration the curvature of the graph, because if you had a function that looked like, you know, something like this, in between 3 and 7, it's pretty flat for most of the intervals, so that's a lot of low y values and doesn't really start to grow until the end. So when functions are curved, you can't just take the beginning and ending y values and average them. So in theory, what we're going to want to do is add up all of the y values in between 3 and 7 and then divide by the number of y values. That's how we average things. So if we wanted to find the average y value for this function, we should add up all the y values and then divide by how many there are. But then, like, how do you add up all these y values? There's an infinite number of y values in between 3 and 7. But, you know, that is what integration does. So when we think about the function y equals x squared in between 3 and 7, so here's 3, what integration is doing, the integration operator, is it's taking the height of an infinite number of infinitely skinny rectangles and adding them up. So each of those rectangles, the height of each of those rectangles is a y value from this function. So as you are adding up, you know, and computing this area underneath the curve, what you're actually doing is adding up all of the y values on this function. So, you know, you keep going, keep going. So when you integrate x squared from 3 to 7, what you are doing is adding up all the y values on that graph. Also turns out to be the area under that curve. So if I integrate x squared from 3 to 7, I will find the sum of all of the y values. So here you can see in this fraction, I went ahead and integrated. The antiderivative x squared is x cubed over 3. And then I plugged in 7 and 3 and took the difference. So then the last part we need to do is to divide by how many numbers are in between 3 and 7. So technically there's like an infinite number of numbers in between 3 and 7. To find the number of values we're going to divide by, we're just going to subtract the end of the interval from the first interval. So here we just do 7 minus 3 and we get 4. So we divide the sum that we got, divide by 4, and that gives us 26.3. So if you graph this, you'll see 26.3. It's like, whew, scared, somewhere right around there. So that's how you do it. So I think there's going to be, oh yeah, so I graphed it. So here's 26, whoops, pen. So here's 26, here's y equals x squared. So that's the average y value. Okay, so I think there's an example for you to try on the next slide. Sure is. So go ahead, give this a whirl, try to find the average value for this function on the interval for 1 to 4. So there's a little word problem that goes along with it. This function represents the balance in a checking account over the course of a year where x is measured in months. So we want to find the average balance in this checking account during that time. So take a whirl, and the solution will appear here in a second. So I'm going to set up the integral first, and then show that to you, make sure you got it, and then we can finish it. So here's the setup for the problem. Here we've got 1 over 4 minus 1. So that's going to be the part where we divide once we find the sum of all the y values. And then this integral is the sum of all the y values of this function. So go ahead and integrate this and get the answer. Okay, so here's the solution. This 1/3 is just the 1 over 4 minus 1, so it's hanging out in front. When you integrate this, you get 3x cubed over 3 minus 2x squared over 2. The coefficients cancel. I plugged in 4 and got 64 minus 16 minus 1 minus 1, and then simplified and got $16. So the average balance in this bank account in between month 1 and 4 is $16. Hooray! So here, these problems are the practice problems for these two topics. These are from the book. It's practice with the new trig rules and some average value functions. So enjoy. Thanks for listening.